we have talked about resting membrane potential. Resting membrane potential was when membrane was negative from inside and positive from outside, and it is due to difference in charges across membrane, that is called as potential difference. So membrane is in case of neurons, muscles and epithelial cells, it depends on type of cell how much it is negative from inside, and mostly the potential difference of charges across the membrane are minus 70 millivolt, minus 90 millivolt, minus 50 millivolt. It depends on the type of cell. So in resting condition there is charge separation. So this charge separation, we know the sodium are more concentrated outside and potassium are more concentrated inside, and proteins and DNA, RNA are more present inside. So inside is negative as compared to outside. So when there is change in this pattern in the membrane potential, during which the potential actually reverse, inside become positive and outside become negative for a brief rapid time. uh, this change in potential is large enough that it is reversing the resting membrane potential on a specific area of membrane, and then this change is spreading on the whole membrane, that is called as an action potential. So action potential just occurs on muscles and nerves only, and it is not occurring on epithelial cells. Resting membrane potential occurs on three tissue types: epithelium, muscle, and the neurons, but action potential only occurs on uh, the muscle cells and neuron cells. So the action, when we define action potentials are brief, rapid, large changes in membrane potential during which the potential actually reverses, so that inside of the excitable cell transiently become more positive than the outside. So there are various stages of action potential. We know them. They are depolarization, repolarization, and then hyperpolarization. So what is the depolarization? In this diagram, we can see that membrane is on resting membrane potential. Here we are looking at an axon. So it is on resting membrane potential, and it has during resting membrane potential the sodium voltage channel. Their activation gates are closed and inactivation gates are open. Potassium channels, they are closed. They are again potassium voltage channels. We have to make one thing clear, that the dendrites, they have sodium channels of any type. They could be mechanical gated channel, voltage gated channel, they could be chemical gated channel. It depends on the stimulus dendrites are receiving. But in axon there are only voltage channel. They are sodium voltage channel, they are potassium voltage channel. So in axon, the when membrane is on resting membrane potential, it is negative from inside and positive from outside. Then this membrane, the sodium channel, they are, their activation gates are closed. Potassium channels activation gate are closed, and membrane is on called as on resting membrane potential. So when there is a triggering event in dendrites, we cannot see dendrites here. So from dendrites, as we described previously, if they are, for example, this neuron is for chemical stimuli. So chemical stimuli, chemical will come and bind with the sodium chemical gated channel on dendrites. So these sodium channels, they will get open, and sodium will come into the dendrites and then into cell bodies. These sodiums, they ions, they will get sum up, they will change potential, but they will get sum up in axon hillock, the area where axon is joining with the cell body. So at that area, if these ions are sufficient, they can open these activation gates of the sodium channel. So if activation gates of sodium channels, voltage channels in axon, they will get open, more sodium will go into the cell. So entry of sodium will decrease this difference of minus 70 millivolt that was attained here, and it will go toward positive. So minus 70 millivolt to the membrane will go toward positive, but before going to positive charges, it has to go uh, to pass from 0 millivolt, because inside and outside now is going to be equal, because first membrane was positive from outside and negative from inside. Now inside has to be negative as compared to outside, has to be positive as compared to the outside. So before going to positive, it has to go to zero charge. The charges become equal outside and inside because of entry of sodium. So this stage is called as depolarization. So depolarization is occurring due to the entry of sodium ions into the cell. So then at the same time, these sodiums ion that have entered into the cell, they will flow in the next segment of the axon, and then they can influence these potassium voltage gate channels and sodium voltage gated channel in next segment. So these channels, they start to open, but potassium channels, they are slower channels, so they'll open slowly. Sodium voltage channel, they are fast channel, they open early, and sodium enters into the next segment of the axon, and then this sodium then flows in the next segment to open other sodium channels and potassium channel. So that is called as depolarization. Inside has become positive and outside as compared to outside. So this is actually reversed to the resting membrane potential. Then it is repolarization. How repolarization occurs? Repolarization is the attainment of the resting membrane potential again. So this happens due to leakage of potassium instead of leakage of sodium that entered. Depolarization occurred due to entry of sodium, and repolarization occurred due to the leakage of potassium. So how potassium goes out? We know these potassium channels, they were potassium voltage channels. They were closed at resting membrane potential. We can see why they were closed, because their gates were negatively charged and inside of the membrane was also negative. So this keep it pushed to keep them closed. But when inside become positive, these negatively charged gates, they start to open, and then potassium, because they are slow, potassium start to leak, and again the inside will become, because these are positive charges, so positive charges are leaking, equal number of positive charges to sodium will leak out, so inside will become negative again. That is called as repolarization. So repolarization occurs due to opening of potassium voltage channels. Then occurs hyperpolarization, because these potassium channels, they are slow to close. So when membrane pass from resting membrane potential, these potassium channels, they are not closed. Potassium keeps on leaking. So inside become more negative because of leakage of potassium. So it inside become more negative as compared to resting membrane potential, and the more negative charges would be called as the hyperpolarization. They go beyond minus 70 millivolt, that was the resting membrane potential. They become minus 90 millivolt, for example. That is called as hyperpolarization. And then this hyperpolarization is adjusted by sodium potassium pump. They push 3 sodium outside and 2 potassium inside, so again they are adjusted. So here we can see this phenomena that this is the outside of the extracellular material and this is the cytoplasm, and here we can see these brownish color of uh, particles, these are potassium, and these bluish, they are sodium. So we can see here that these blue are sodium channel and brown are the potassium channel. And here we have put a voltmeter. So this voltmeter, when we put one electrode inside of the cell and one outside, it shows the potential difference, how much charge difference is present along the membrane. So on resting, when there is it is exon. So on resting condition, the charges are minus 70 millivolt. So when there is no conduction of charges, it is minus 70 millivolt. It means inside is more negative. It has minus 70 millivolt potential difference. So when the exons, the dendrites, they conduct sodium ions, and they are sufficient to open to influence these sodium channel. They get open, sodium enters into the cell. Here we'll see now sodium enters into the cell, and then the this sodium, it goes into the next segment, open potassium channel to lose potassium outside, but at the same time they open sodium channel in the next segment. So these are voltage channels. So these sodium channel, they get open and sodium enters into the cell, and along with that we can see here change in potential. For example, this sodium channel get open, then there will be change in potential that goes minus 70 millivolt to 0 millivolt, and then to up to 20 plus 20 millivolt, because sodium are positive, they are entering into the cell, making it more positive. So membrane go to 0 and then to the plus 20 millivolt. It is less than uh, 70 millivolts, so it is called as depolarization. And then there is repolarization. Repolarization is due to opening of these potassium channel. You can see here, when potassium channel get open, the membrane goes back to minus 70 millivolt. You can see here now. So then the membrane is also going toward the hyperpolarization. Here we can see, so that is due to slow potassium channels. Here is another view of the process of action potential. Here the we have plotted the voltage potential difference across membrane with time. So the before the process of action potential, the membrane is on resting membrane potential, it is near to minus 70 millivolt, and here we can see is 0 and then is plus 20. So the when there is a stimulus and this stimulus is strong enough that it has entered sufficient ions into dendrites, then these dendrites, these ions, they reach to axon hillock, and where they could open sodium voltage channel. Sodium start to enter into the cell, and then there is a depolarization. So there occurs a depolarization, mean due to entry of sodium, these negative charges inside of the membrane, they are going to decrease. Our difference of charges is between cell inside of the cell and outside of the cell is decreasing. So it is going towards 0. So it is called as depolarization, and it occurs due to opening of only the sodium channels. And then we can say if these depolarization, they are sufficient enough, they will open other sodium channels, and due to that more sodium enters into the membrane, and membrane become more depolarized. It goes up to plus 20 millivolt. At plus 20 millivolt, why this membrane is not going toward plus 30? Why the depolarization is occurring till plus 20? Because we saw the sodium channels, they have inactivation gates. So these inactivation gates, they are made up of positive amino acids. So at positive charge of plus 20, these inactivation gates, they are plugged into the sodium channel. So sodium channel, they become inactivated. They cannot conduct more sodium into the cell until the channels, the membrane reaches to back to the resting membrane potential. So then we said there is a repolarization phase. In repolarization phase, the potassium channels, they get open. They are slower channels, so they get open and start to conduct potassium outside of the cell. So membrane is now, because positive charges, potassium charges, they are going out, so membrane is again going toward negative from inside. So it will goes on, and then it reaches to the resting membrane potential, that is called as repolarization. But it is not stopping at the resting membrane potential, because the potassium channels, they are slower channels, so they will make membrane more negative than the resting membrane potential. So that is called as hyperpolarization. Here once again we see the configuration of sodium voltage channels. We know the sodium voltage channel in exon, they have inactivation gate and an activation gate. This activation gate is made up of amino acids that are negative in charge. So at resting membrane potential, this negative gate is pushed by negative ions inside the cell, and these gates, they are closed. These inactivation gates of sodium, they are made up of positive amino acids. So when there is resting membrane potential, mean inside of the membrane is negative, these charges, they keep open the inactivation gate open. So no more sodium can enter into the cell due to the closure of the activation gate at resting membrane potential. So at resting membrane potential, it is minus 70 millivolt. Here the sodium gates or sodium channels are closed. But when sodium enters from dendrites, it reaches to here, and it has they have been summed up in exon lock. They are enough and they can attract, because the sodium sodium ions, they are positive, so they can open this activation gate, because this activation gate is made up of negative amino acids. So these positive charges, if they reach from exon hillock here, they can open this activation gate. And if the open activation gate, more sodium enters into the cell, and the membrane become positive. It goes from minus 50 millivolt to plus 30 millivolt, for example. And at plus 30 millivolt, for example, these charges, the positive charges, they are now enough. They will push this inactivation gate, because it is made up of positive amino acid. So these positive charges, they will push it back into the sodium channel, and no more sodium can enter into the cell. So when membrane or axon has reached to a segment of axon has reached to the plus 30 millivolt, it cannot conduct more sodium into this segment. So these channels, they become inactivated, and then these sodium channels, they will diffuse in the next segment and open other sodium voltage channel, that are the activation gate of other sodium channels, but not these sodium channels, because their inactivation gates are plugged and they are positive. So positive ions cannot open these positive, cannot pull them, because they are to push them into the tunnel. Again for potassium channel, at resting, because the potassium channel, they are made up of only one gate, that is the activation gate. It is made up of negative amino acid. So when membrane is at resting membrane potential, that is minus 70 millivolt, these potassium channel, they are shut, because they are made up of negative amino acid, negative inside. So these charges, they keep them shut. And when sodium enters into the cell, the cell inside become positive. Here positive charges come, they will pull the activation gate to open it. So at plus 30 millivolt, the potassium channels they start to open and potassium is going outside of the cell. So when this membrane will reach back to the uh, resting membrane potential, that is minus 70 millivolt or minus 80 millivolt, that is hyperpolarization, then these charges they will push these potassium channel to go and get closed. So no more potassium will go out, so membrane will not go beyond minus 80 millivolt. So again we have to define a few terms that are related to stimuli, and there are few other terms. The stimulus we know is a triggering event. It is the change that can change the action, the resting membrane potential to produce electrical signal. So a stimulus, if it can open insufficient number of sodium channels in dendrites, then they cannot produce action potential in axon. So this type of stimuli, they are weak stimuli. They are called as subthreshold stimuli. They cannot bring membrane up to a level that sodium voltage channel gates could be open in axon. So the ions that enter from the dendrites, they get diffused and they cannot reach to axon to open sodium voltage channel. So sodium voltage channel they remain closed. There is no action potential. Threshold stimuli are stimuli that are enough to open sufficient number of sodium channels in dendrite so that a lot of sodium ions enter into the dendrite, they get sum up and they are sufficient to open the activation gate of sodium channel voltage channel in axon to produce action potential in axon. So if stimulus is of threshold level, then the action potential that are produced on a membrane, they depolarize up to a certain level. For example, if membrane is at minus 70 millivolt, it will always go to, for example, plus 30 millivolt and then back to minus 70 millivolt. If stimulus is stronger than this level, that is called as suprathreshold stimulus, it cannot bring membrane to plus 40 millivolt because whenever membrane will reach to plus 30 millivolt, we know these sodium voltage gates they get plugged. No more sodium can enter into the cell to make it plus 40. So it will always stop at plus 30 millivolt, and then due to opening of potassium voltage channel, it will go back to minus 70 millivolt. That is the suprathreshold level of stimuli. They can even produce same magnitude of action potential. It means membrane can depolarize up to a level that is fixed. It is same for threshold level of stimulus or greater than threshold level of stimulus. That is called as all or non-law. Either action potential will be produced or not. If it is produced, then it will be of same magnitude, even stimulus is of threshold level or suprathreshold level. And in case of subthreshold level of stimulus, action potential will not be produced. So that is called as graded potential. It is not action potential. So it will diffuse out if it is subthreshold level of stimulus. What is refractory period? Again, when these sodium voltage channel, they their inactivation gate get closed due to positive ion present inside membrane due to entry of sodium. These positive charges, until they are because these are positive charges, and then these activation inactivation gate, they are also made up of positive amino acids. So these positive charges, they will not allow these inactivation gates to get open. So when potassium leak out, membrane will go toward negative, and when it reaches to resting membrane potential, that is minus charges are attained inside the membrane, then these inactivation gates are pulled back. Before this reaching membrane back to resting membrane potential, these channels, they cannot conduct sodium into the cell. So if another stimulus comes, then these sodium ions, they will go into the dendrites, they will summed up, they will reach to axon lock and to the voltage channel. But these voltage channel, they are already closed due to presence of sodium ion or positive ion. Now entry of more sodium ions cannot open these channels, so these channels will remain closed, so there will be no conduction of action potential for a brief time. That is called refractory period or resting period of the neurons or muscle cells. So during refractory period, the neurons only, the neurons, they are not conducting action potential, even the stimulus is present. And sometime with the fraction of time, even suprathreshold level of stimuli, they cannot open these channels. So this process is called as refractory period. So refractory period is divided into two types: absolute refractory period and the relative refractory period. During absolute refractory period, the membrane is at highly positive charges, that is just it has depolarized, so it is up to, for example, at plus 30 millivolt. So if suprathreshold level of stimulus can occur, is occurring again, it cannot even open the sodium voltage channel. That is called as absolute refractory period, that is the must refractory period. So during this, for example, the absolute refractory period is about 1 millisecond, and the after that the membranes start to go from plus 30 to negative towards zero due to leakage of potassium out of this cell. So when it is going toward negative, now there are less positive charges and more negative charges inside. So if a threshold level of stimulus comes, it will be summed up in axon lock. It will cause these channels to not open. It cannot, threshold level of stimulus cannot open. These charges are insufficient to open these channels. So if there comes a suprathreshold level of stimulus, they can open these channels again, and to start the conduction of action potential again. So that is called as, that period is called as relative threshold level of stimulus. It is about 9 millivolt after passage of the action potential from the membrane. So now we know suprathreshold stimulus produces equal magnitude of action potential, but it can produce action potential in refractory period, relative refractory period also. So suprathreshold level of stimulus, what it does, it increases frequency of action potential on a membrane, not the magnitude of action potential on the membrane. So the magnitude of action potential remains same, but number of action potential are increased on the cell membrane if there is a suprathreshold level of stimulus. Here we have to sum up whole process of resting membrane potential and action potential. We said in neurons, the dendrites, they are receiving stimuli. So there are sodium channel on dendrites. These sodium channel, they are either mechanical, voltage or chemical gated channel. Axons, they have only potassium voltage gated channel and sodium voltage gated channel, and at the end of neurons there are calcium voltage gated channel, but calcium voltage gated channel, they don't have to do anything with action potential. They are just related with the release of neurotransmitter. We will see them later on. So the axon, they are having voltage gated channel. These voltage gated channel, as we saw, they are sensitive to voltage, change in voltage. They are closed. For example, for sodium voltage gated channel, they have activation gate and inactivation gate. Their inactivation gate are made up of positive amino acid, and their activation gate are made up of negative amino acids. So activation gate, when membrane is on resting membrane potential, are negative from inside or closed, and inactivation gate are open because they are made up of positive amino acid, and inside of the membrane at resting membrane potential is positive, sorry, negative. So these positive gates, they are pulled and they are open. The potassium gates, they are only activation gate. They are again made up of negative amino acids, so they are closed at the negative resting membrane potential. So when the stimuli, they are of the uh, sub-threshold level, then sodium ions enter into the dendrites. They are entering from different dendrites at different time, and they are summing up here at the axon hillock. But if they are insufficient ions, they cannot open the sodium voltage channel here. So these ions that have entered, they will diffuse out. So that is called as graded potential, or that is called as the degenerative potential, because it is degenerating along the membrane. It is not spreading on the whole membrane because it cannot open sodium voltage channels here. If these ions are sufficient, because the stimulus is of threshold level, and these sodium ions, they will summed up, they will open sodium voltage channel here, their activation gates, and then sodium will rush into the cell at this segment. These sodium ions, then they will spread into the next segment of the axon. But at this segment, when these sodium ions, for example, they reach up to the level of plus, here we can see it is up to plus 30 millivolt, these inactivation gates, they are positive, they will get closed and no more sodium is entering here. So that is the optimal depolarization occurred here. So after the depolarization of this area, then these charges, they flow in the next segment, and they open potassium channel here and the sodium channel in the next segment. So potassium channel, they are slow to open, so they will get open and potassium will start to leak out. The meanwhile, the sodium channel in the next segment, they start to open. So here depolarization start, and repolarization start due to opening of potassium channel, and depolarization start in the next segment due to opening of sodium channel. So in previous section, it is repolarized, or the membrane goes to hyperpolarization due to the potassium slow channel, and in the next segment it is depolarization. So this cascade of depolarization, repolarization, then depolarization, repolarization, it runs up to the level of the axon end, that is the axon knob, or the synapse, or neuromuscular junction. What happens at neuromuscular junction is to release the neurotransmitter. We see them in later section.